If you really want to understand MRI, you have to understand magnetism. In a standard clinical MRI, the machine is imaging your water. Every water molecule has 2 protons, and each proton is a little magnet. We're going to run a little thought experiment. Let's imagine you have a little bulb, an electric light bulb from a flashlight, and that bulb is connected to a wire. And then underneath that wire you have a little stand, and on that stand is a little magnet. You know, one of those old bar magnets? You flick the wire, and the magnet spins. What that will do is it will induce a current in that wire, an oscillating current, yes, and the light will go on, it'll flicker. You'll generate a current just by spinning a magnet underneath a wire. Now in the MRI, the piece of the MRI that goes over your body, the RF coil, or the coil they call it, what it does do is it picks up signal from all the spinning magnets in your body. When you spin the nucleus of the proton underneath that RF coil, you get a current in the coil. But how does it all happen? And here's where the big magnet comes in. Imagine that each one of your protons is a spinning little magnet, and it's spinning away and spinning away. And then you put it in a magnetic field that's oriented. It's along the bore of the magnet, it's along the axis of the magnet, and those spins start to realign along the magnet. Now normally that nucleus is just randomly spinning. All the billions and billions of them are spinning. You put them in a magnetic field, and some of them, it's a probability distribution, but some of them will reorient, and they'll be spinning on the axis of the field. In fact, the signal in MRI goes up in proportion to the magnetic field strength, just for that reason. More of these protons, as they're spinning, spin the same. Now you're lying in the magnet, your protons have oriented along the axis of the field, but the RF coil, the coil that's around you, has an orientation that goes sideways. So these spins aren't generating a current. Now that coil can generate a local magnetic field and reorient the spins. Now the spins are under the coil like this. Now they're generating a current. That current goes back to the amplifiers. Amplifiers are detected by the computer, analyzed, create signal. But now you've got signal. You don't have an image. There are local electromagnets around the bore of the magnet, so that you can generate a gradient of magnetic field across the axis or along the axis, or in fact on any orientation within the bore of the magnet itself, so that you can generate a condition where at any one spot in the magnet there's a unique magnetic field. Now remember, I said that those protons spin at a frequency that is totally dependent on the field they're in. So if you then collect all the signal and you measure how much signal is at each frequency, you can put the magnitude of that signal at that frequency. And now frequency is space. Remember? Unique magnetic field strength, unique frequency. You can recreate the image if you know how much signal came from every specific frequency. The banging that you hear in the MRI is the change in the gradients. So remember, the gradients are going across the magnet, they're generating local fields across the magnet, but they need to change orientation, at least to have 3 orientations, in order to figure out where in 3-dimensional space your signal's coming from. As the electromagnets change orientation relative to the main magnetic field, there's a slight twisting in the magnet, and you hear that as a banging. So if the gradients change slowly, the banging is quieter. If they change quickly, you hear a kind of a da-da-da sound. When you're lying in the magnet listening to those patterns, you know that the MR technologist is changing the imaging technique, and you get an image.